exercise 3. I know that we've been doing examples and then all of a sudden we started exercising, but just go with it. Determine whether the series summation from n equals 2 to infinity of 1 over n times the natural log of n converges or diverges. What? 2? Why are we starting at 2? Well, the reason why we're starting at 2 is because if we started at 1, we'd make a black hole in space and time. If I stuck 1 in the denominator here, oh, sure, the outside is fine. Where's the laser pointing? Come on, where's the laser pointing? Where's the... there it goes. Yeah, sure, that's fine, but the natural log of 1, that's 0. We'd be dividing by 0. All right, so this sequence is going to start at 2 instead. Does it matter? Can we still use the integral test? I think so. Let's go ahead and try to apply that. Before we can apply the integral test, we have to make sure. I'm gonna go ahead and say that it's an example instead of an exercise. Example 3, and we have 1 over n natural log of n. We're going to consider instead the function 1 over x natural log of x. And then we want to make sure, is it positive? Is it continuous? Is it decreasing? And in this case, it's going to be for n greater than or equal to 2 instead of 1. Well, the whole entire reason why we're starting the other ones at 1 is because that's usually where those sequence, the first term was starting. Anyway, is it, number 1, is it positive? Well, if I look at f of x is equaling 1 over n times the natural log, well, no, x. Natural log of x. Okay, if I were to stick in a value for my x, realize your x value is 2 or bigger, that part's always positive. All right, so that part's fine. But what about the natural log part of it? Well, think of the graph for the natural log. Right? And then here. So it starts being positive right here after 1. So there's 1, and then it's positive everywhere else. Why? I'm not going to use that one. I'll use a broop. So it's always positive for greater than 1. So we're good. So I'm going to conclude that this is greater than 0 for x is greater than or equal to 2. And our first condition has been satisfactorily met. Satisfactorily? Yeah. Number 2, is it continuous? All right, so the continuity on this part may be a little bit different than, say, the rational function. This is not rational. Rational has to be polynomial divided by polynomial. But we kind of treat it the same way. The only place where we would have asymptotes would be at 0. And on this one at x equals 1. Well, both of those are outside of where we're considering this. So it is continuous everywhere greater than or equal to 2. These are the only two asymptotes here. So f of x is continuous for x greater than or equal to 2. Another reason why we couldn't have started at 1. There's a vertical asymptote there, right? All right, and then is it decreasing? We will look at the derivative. So I will rewrite this so I can avoid using some weird quotient rule stuff with 1 on the top as x natural log of x to the negative 1 power, and then use some chain rule action on it. Negative x natural log of x to the negative 2 power, and then I need to multiply it times the derivative of the interior, and in order to do that, I will have to use the product rule. Derivative of the first is 1 times the second, natural log of x, plus the first one, which is x, times the derivative of the second one, which is 1 over x. That's just going to be 1. There you go. And maybe rewrite this thing. I would have negative, I'll keep the negative on top, natural log of x plus 1 over x natural log x quantity squared. Okay, well, that guy is always positive. right? And then the top, the natural log of x is always positive, as we saw over here, greater than 1, and we are sticking in 2, so this is positive, but we're multiplying it by a negative number on the outside, which makes this derivative less than 0 for x is greater than or equal to 2. And we needed that because if it's less than 0, first derivative, that means our function is decreasing, since f prime of x is less than 0 for x is greater than or equal to 2, f of x is decreasing. And I have checked off, I didn't check this one off, so I'll check it off now. Checked off the decreasing portion. All right, we're good to go with our conditions. All three of them are met. So let's now take the improper integral from not 1, no way, 2 to infinity of 1 over x natural log of x dx. Make sure that you turn that into a limit as b goes to infinity. Definite integral from 2 to b of, I'm going to go ahead and throw that dx up top, x natural log x. And guess what? Guess what? It's another u substitution. U is equal to the natural log of x, because the derivative of u would be equal to 1 over x, and that's what I've got right here. Why did I color that in like that? I don't know. I meant to do this. Right? That dx over x. Oh yeah, I do need this on here, a dx. Right? So again, I don't even have anything to compensate for. This is a du over u, which is the natural log of the absolute value of u, equals the limit as b goes to infinity of the natural log of the absolute value of, well, what's our u? The natural log of x. Boom. Evaluated from 2 to b. It's kind of like an inception of natural logs. The natural log of the natural log. All right, let's plug our stuff in. Limit as b goes to infinity of the natural log of the absolute value of the natural log of b minus the natural log of the absolute value of the natural log of 2. Boop. All right, and then when we plug in our infinity, right inside here, the natural log of infinity, that's infinity. We're taking the natural log of that again. It's still infinity minus, it doesn't even matter. This diverges. All right, if that improper integral diverges and our function is, the function that we use to represent it is positive, continuous, and decreasing by the integral test, our series must also diverge, since f of x is positive, continuous, and decreasing for x is greater than or equal to 2, and the definite integral, that looks like an S, definite integral from 2 to infinity of 1 over x natural log of x dx diverges. Then the sum from n equals 1 to infinity of 1 over n natural log of n also diverges by our friend, the integral test. And we're done. All right, that's about it for this particular video. When we come back, let's define these things called p-series and come up with the p-series test.